In many industrial facilities, various pieces of equipment, as well as many fluids used in process systems, need to be cooled. In many cases, the cooling of equipment and process fluids is done with water. But as cooling water is used, it absorbs heat and its cooling effectiveness decreases. Disposing of or discharging the hot water into lakes or rivers can lead to thermal pollution. Also, water that is discharged must be replaced, which may be costly. For these reasons, it's often more efficient to cool the hot water and reuse it. The device that's most commonly used to do this is a cooling tower. Cooling towers are often used as part of a cooling water system in a facility. The system may be used to cool many different components and process fluids. This illustration shows a simplified system that includes a cooling tower, a circulating pump, a shell and tube heat exchanger, and fluid lines. In this system, cool water is pumped from the bottom of the cooling tower to the heat exchanger. In the heat exchanger, heat from a process fluid is transferred to the cooling water. After absorbing heat from the process fluid, the water flows from the heat exchanger to the top of the cooling tower. The water then falls through the tower and is exposed to air, which cools the water. The cooled water collects at the bottom of the tower and is pumped back through the system for reuse. Now, as we just said, cooling towers cool water by exposing it to air. Exposing the water to air causes some of the water to evaporate. In fact, most of the cooling that takes place in a cooling tower is a result of evaporation. Evaporation is a process in which the heat in the water causes part of the water to turn into vapor. As the water is turned into vapor, the heat is removed. As a result, the remaining water is cooled. In a cooling tower, heat that was in the water leaves the tower in the vapor as the water evaporates. Conduction and convection also play a role in a cooling tower. In the tower, water comes into direct contact with the air. When this occurs, some of the heat in the water is transferred to the air by conduction and convection. As much as 1/3 of the heat that's transferred in a cooling tower may be a direct result of conduction and convection heat transfer. Even though all cooling towers operate on the same basic principles, their designs can be divided into two broad categories: natural draft towers and mechanical draft towers. The term draft refers to the flow of air through the tower. In a natural draft cooling tower, air flows through the unit naturally without the aid of mechanical devices. As the water evaporates and heats the air inside the tower becomes warmer and less dense than the air surrounding the tower. As the less dense warm air rises up through the tower, denser, cooler outside air is drawn into the bottom of the tower. In contrast to a natural draft tower, airflow through a mechanical draft tower is created by using one or more fans. In an induced draft cooling tower, the fans on top of the tower create an area of low pressure. This causes the air to flow in through the sides of the tower and up to the top of the tower. In this cooling tower, water enters through inlet pipes and is spread out in troughs. Distribution nozzles direct the water from the troughs onto packing inside the tower. The packing slows down the water as it falls through the tower. It also breaks the water up into small droplets. Both of these actions promote better heat transfer inside the tower. As the water cascades down through the tower across the layers of packing, a fan draws the air in through a set of louvers, around the packing, and then through a drift eliminator. The drift eliminator traps water droplets that could be carried along with the air as it passes out of the tower. By the time the water reaches the catch basin, it's cool. The cooled water is then drawn out of the tower through the outlet line and pumped back to plant equipment for reuse. Now that we've seen how an induced draft tower operates, let's take a look at another type of mechanical draft tower. This one is called a forced draft cooling tower. The major difference between an induced draft tower and a forced draft tower is that a forced draft tower does not create an area of low pressure that draws air up through the tower. Instead, the fans force or push the air up through the tower. On this tower, there are no louvers on the sides. Instead, there are fans with screens that direct the flow of air into the tower. So, as the cooling water cascades down from the top of the tower, the fans force air up through the tower and the heat transfer process takes place. Now, regardless of the type of cooling tower, there are some components that are common to most towers. For example, many towers are divided into sections called cells. This tower has 3 cells. Each cell contains all of the components of a single tower, except they share a common catch basin. Each cell of a tower can be operated independently, so the proper amount of cooling can be maintained by taking one or more of the cells out of service or placing them in service. Other components, such as blowdown and makeup lines, are also important to a cooling tower's operation. These components deal with the condition of the cooling water. The water in a cooling tower often contains impurities that can cause problems. As the water in the tower evaporates, the concentration of the impurities increases. To control the concentration of impurities, water is periodically discharged from the catch basin through the blowdown line. This water is then replaced with clean water through the makeup line. On this cooling tower, the flow through the makeup line is controlled by a control valve. A float senses the level in the catch basin. As the level changes, the float moves and sends a signal to the control valve, which opens or closes to regulate the flow of water through the makeup line. In this topic, we looked at how a cooling tower can be used in a cooling system, and we talked about how heat is transferred inside a cooling tower. We also looked at different types of cooling towers and at some of the components that are common to many cooling towers. Now let's try some practice questions. In this topic, we looked at how a cooling tower can be used in a cooling system, and we talked about how heat is transferred inside a cooling tower. We also looked at different types of cooling towers and at some of the components that are common to many cooling towers. Now let's try some practice questions. There are several basic steps involved in shutting down and starting up a cooling tower cell. Since cooling towers are important to many processes, you need to know how to properly place a cell in service and take it out of service. The steps we'll cover are often followed in startup and shutdown procedures. But be sure to follow your facility's operating procedures when you're starting up or shutting down a cooling tower cell. You should also be aware of the impact that shutting down or starting up a cell will have on the processes. First, the operator checks a temperature recorder to see if the cooling tower will be able to cool the cooling water sufficiently with one less cell in service. Once he's sure that the remaining cells will cool the water, he shuts off the fan and opens its breaker. He then tags out the breaker to warn other workers not to reset it. Then the operator closes the valve on the inlet line to the cell's trough. Once the valve is shut, the cell is out of service. Once the cell is shut down, the operator monitors the operation of the cooling tower to ensure that the cells in service are properly cooling the water. When the operator is informed that additional cooling is needed, he begins the startup of the cell. First, he opens the valve on the inlet line to the cell's trough. This fills the trough with water, and the water starts to cascade through the cell. Then the operator removes the tag from the breaker, closes the breaker, and restarts the fan. Once the fan is up to speed, the cell is back in service. When a cooling tower is in service, it's important to check it for proper operation. As an operator, there are several routine checks that you can make to ensure that the tower is operating properly. One thing to check is the water level in the catch basin. If the level is too low, the circulating pump could lose suction. That could damage the pump and reduce or stop the flow of circulating water. The level in the catch basin is sensed by floats in the basin. Operators should check the floats to make sure they move freely so that the proper level can be maintained in the basin. While checking the water level in the catch basin, Operators should also check the appearance of the water. If the cooling water is murky or if it has a film on it, there may be a problem with the cooling water system, such as a leak in one of the heat exchangers. The pump and its driver should be checked for unusual noises, excessive vibration, and overheating. The lubrication of the driver and pump should be checked as well. Often, screens or filters are placed in front of a pump suction. Screens are used to prevent trash or other foreign material from entering the pump. A plugged screen could restrict water flow into the pump and cause the pump discharge pressure to drop below normal. To prevent this problem, the screen should be checked and cleaned or replaced periodically. Another thing on a cooling tower that should be checked is the spray from the nozzles. In order for the tower to cool efficiently, the water has to be distributed evenly over the packing. If the pattern of water falling over the packing is irregular or contains gaps, it's an indication that nozzles may be blocked or clogged. While checking the water falling through the tower, it's also a good idea to check the packing for damage. The fan, along with its gearbox and driver, should also be checked for unusual noises, excessive vibration, and overheating. Also, the lubrication of the fan and driver should be checked. In addition to the checks we've just covered, it's also important for operators to regularly monitor cooling water temperatures and pressures to make sure they're within normal ranges. For example, the discharge pressure of the circulating pump should be checked to ensure proper flow through the system. Also, water temperature should be checked to see if the correct amount of cooling is taking place. In this topic, we looked at the basic steps involved in shutting down and starting up a typical cooling tower cell. We also watched an operator make some basic checks on an operating cooling tower. Now let's try some practice questions on this material. All cooling water contains contaminants. The contaminants in cooling water can be divided into 4 broad groups: suspended solids, dissolved gases, and microorganisms. Suspended solids are solid particles that are trapped in the cooling water. One source of these particles is air. Dust and dirt can be carried into the tower by the air passing through it. These particles become trapped or suspended in the cascading water. Another source of suspended solids is the makeup water. Solids are carried into the tower as water is replaced. When suspended solids collect inside a cooling water system, they form a thick mixture called sludge. Sludge can restrict water flow through equipment, interfere with the transfer of heat, and decrease cooling tower efficiency. Chemicals such as calcium or magnesium are often found as dissolved solids in cooling water. These impurities can become concentrated, come out of solution, and cause scale buildup. Scale buildup on the inside of a heat exchanger can reduce heat transfer and restrict water flow. Now, there are several ways that dissolved solids can concentrate to form scale. For example, when water evaporates in a cooling tower, the solids are left behind, and the concentration of solids becomes higher in the remaining water. Also, untreated makeup water may have high concentrations of dissolved solids. One way to control the concentration of solids in a cooling tower is to drain or blow down water from the system. A blowdown is an intentional discharge of cooling water from the catch basin. In addition to blowdown, scale-preventing chemicals may be added to the cooling water to control scale buildup. These chemicals, known as scale inhibitors, form a protective layer on metal surfaces that prevents scale from building up. Other chemicals may be added to control the water's pH. The water's pH is an indication of its acidity or alkalinity. A low pH means the water is acidic. A high pH means the water is alkaline. A relatively low pH tends to increase the likelihood of corrosion, while a relatively high pH tends to increase the likelihood of scale formation. If the water's pH is high, acids such as sulfuric acid, which have a low pH, can be added to lower the water's pH. On the other hand, if the pH is too low, an alkali is added to raise the water's pH. Cooling water is often sampled and tested for solids concentration and pH. The results of the tests determine how often blowdown should be done, how much water should be blown down, and the amounts and types of chemicals that should be added. Another group of contaminants that you should be aware of is dissolved gases. Cooling water often contains dissolved gases such as carbon dioxide, hydrogen sulfide, and oxygen. Some of these gases can react with the metal in the cooling system to cause or speed up corrosion. Large amounts of some dissolved gases tend to make the water acidic, giving it a low pH. At a lower pH, corrosion is more likely to occur. To counter the effects of dissolved gases, corrosion inhibitors, such as lime, are often added to interfere with the corrosion process or increase the water's pH. Your cooling system may have specific operating requirements for pH. These requirements will strike a balance between a high pH that will reduce the rate of corrosion and a low pH that will reduce the rate of scale formation. Microorganisms are very small plants and animals, such as algae and bacteria. Air and sunlight stimulate microorganism growth, so cooling towers make good breeding grounds. Microorganisms often create thick, gummy slime growths that can foul tubes and heat exchangers and reduce the amount of heat that can be transferred. Another problem with microorganisms is that they can release gases such as oxygen inside cooling systems. This can promote corrosion of the equipment in the system. Microorganisms can be controlled by adding chemicals called biocides. Chlorine is one biocide that's commonly added to water to prevent slime growths. Chemicals are added to the water in cooling towers for many reasons. You may be responsible for adding chemicals to the water, so you need to know how to do it safely. Many of the chemicals used may be hazardous if they're not handled properly. You should always be aware of their specific hazards, and you should follow your company's procedures when you handle any chemical. The precautions you need to take may depend on how the chemicals are added. For example, some chemicals can be added so that there's no contact with personnel. Chemicals such as acids are added using chemical injection pumps like this one. On this pump, the amount of chemicals added can be controlled by adjusting the stroke of the pump. That's done by turning this knob on the pump's controller. Chemicals are sometimes added using specialized metering devices. Here, chlorine is added to the cooling water through this chlorinator. A chlorinator regulates the flow of chlorine gas to the cooling water system. The chlorinator allows chemicals to be added in such a way that personnel do not come into direct contact with the chemicals. Now, chemicals aren't always added with specialized equipment. Sometimes you have to add them by hand. If that's the case, you'll need to follow your company's procedures about where and how the chemicals should be added. For example, you may be required to add the chemicals near the makeup line so that they can be thoroughly mixed with the cooling water. Depending on the type of chemical that you work with, a face shield, rubber apron, gloves, and boots may be required to protect your body. In some situations, the chemicals being added may be in the form of a powder, so a dust mask or a respirator may be needed in addition to eye protection and other protective gear. Also, you should know the location of the nearest emergency shower and eye wash stations.